Hello, this is Sergio Gomez. My UFID is 2832878. Today is 5/31/2022. This is lab number 3 for EEL 3110C, and this is for Tevian and Norton equivalent circuits.
Hello, my name is Naya Sanchez Lucero, and my Panther ID is 6115497. For activity 1, we were tasked with finding the Thevenin and Norton equivalents of a given circuit meeting certain conditions. And to meet those conditions, we set R1 equal to 1 kilo ohm, R2 equal to 3 kilo ohms, and the voltage source equal to 5 volts. In order to find the Thevenin resistance, we used the equivalent resistance method by short-circuiting the voltage source. And the resistors are in series, so they are additive, and we got a Thevenin resistance of 4 kilo ohms. Then we short-circuited the circuit to find the current. And here I used mesh current analysis, and I ended up with a current of 5 milliamps. Then we used Ohm's law to find the Thevenin voltage, which gave us 20 volts. And as you can see on the screen, we have the Thevenin equivalent circuit with a voltage source of 20 volts and the resistor with a value of 4 kilo ohms. For the Norton equivalent, the resistance is equal to the Thevenin resistance, which is 4 kilo ohms. And then we use Ohm's law to find the value of the current, which is 5 milliamps. For the Thevenin circuit, the voltage and the resistor are in series, and for the Norton circuit, we have the current source and the resistor in parallel. And that's it for me.
So this is the multi-sim for activity 1. This is the current circuit prior to us setting it up for Norton or otherwise. This is a simulation. So with the simulation, we have an amperage of 5 milliamps. So then after we turn off the simulation, this is the Thevenin version. If we do a simulation, you'll see that we end up with 5 milliamps. And then if we do the Norton simulation, we also end up with 5 milliamps. So these are all equivalent. So for the second activity, we had a given circuit where we set the first resistor to kilo ohm, the second resistor to 3 kilo ohms, and the third resistor we went ahead and set to 1 kilo ohms with a 5 volt voltage for the voltage source. We're supposed to find the Thevenin and Norton equivalent circuits. In order to do this, we went ahead and followed the same procedure as we did in activity 1, where we went ahead and shorted out the voltage to find the equivalent resistance within the circuit, which ended up being 1.75 kilo ohms. Thereafter, we went ahead and shorted the circuit to find the amperage of the short circuit. We used loop analysis to determine the amperages within each of the circuits. So we ended up with an amperage of IFC of equaling to 2.14 amps. I mean milliamps, 2.14 milliamps. With that, we went ahead and set up the Thevenin circuit with we actually used the V equals I times R with the 1.75 kilo ohm theoretical resistance and the short circuit of 2.14 milliamps to find a theoretical voltage of 3.76 volts. With that, we used those numbers to set up the Thevenin equivalent, which is on the screen right there, of 3.75 volts and a R theoretical in series of 1.75 kilo ohms. Now the Norton equivalent is just the amperage of that circuit, which in our case would be V divided by R, so 3.76 divided by 1, or 3.75 divided by 1.75 kilo ohms gives us 2.14 milliamps. So that is in the second one with the Norton equivalent, and that ends up being in parallel with the resistor of the Norton, which is 1.75 kilo ohms. For the second part of the problem, we went ahead and had the same problem, except now we set resistor 3 since it was on a potentiometer to 2 kilo ohms. And we solved it the same way we solved for the first circuit, which meant that we found the R theoretical by shorting out the voltage. After we shorted out the voltage, we went ahead and determined that our total theoretical voltage ended up being 2.75 kilo ohms. With the 2.75 kilo ohms, we left that there, and then we moved over to short circuiting the entire circuit. With the entire circuit short circuited, we ended up finding out that we had a amperage of 1.36 milliamps. Now, with this 1.36 milliamps and the theoretical resistance of 2.75 kilo ohms, we use Ohm's law once again to find a voltage theoretical of 3.75 volts. So we went ahead and presented it here on the Thevenin equivalent. So 3.74 theoretical voltage with a resistance of 2.75 kilo ohms. Now, once again, we went ahead and converted that over for the Norton equivalent by using V equals I times R. We found the equivalent amperage to be 2.14 milliamps, presented there with the parallel resistance of 2.75 kilo ohms. So now I will go ahead and present to you the multi-sims for the problem. Starting off here, we have the 2A. So this is with the 1 kilo ohm resistor. If I run a simulation of this, you will find a voltage 3.75 volts and an amperage of 2.143 milliamps. Now, if I turn off the simulation and I go to our Thevenin equivalent and I run a simulation, so we end up with 3.76 volts and an amperage of 2.149 milliamps, well within what we said it would be. For this case, at least the 3.75 volts. Now, if we check the Norton equivalent, we go over here. So I'm going to turn off the simulation. And with this, we're going to go ahead and turn the simulation on for this guy. So we have the 2.14 milliamps, 3.745 volts. So these are in line with each other. Now I'm going to go ahead and turn off the simulation, and this will be 1B where we switch the resistance over to 2 kilo ohms. And if we run the simulation, we have 3.75 volts, which falls in line with what we were saying earlier. And then lastly, we'll go back over to turn off the simulation. Here is our Thevenin equivalent, run our simulation, 3.75 volts, turn off our simulation, go over to our Norton equivalent and run it. .75 volts. So these all fall in line with what we were saying earlier. What's interestingly enough, whether we had the resistance value for R3 equal to 1 kilo ohm or 2 kilo ohms, and this is kind of where we come into our conclusion, they end up effectively being the same theoretical circuit, which is interesting because you would assume that having that resistance value being different would cause a very large impact to the circuit. But it seems as if due to the nature of the circuit, what only really matters is what's on the left-hand side of the circuit, and that resistor value doesn't have a very large impact on the overall circuit. The benefit of using Thevenin and Norton equivalent circuits is that we can use very simplified voltage and resistor in series, or amperage and resistor in parallel, to represent a much more complex circuit that is easier to model for analysis purposes. And that's one of the benefits of using this style of circuit development. Thank you for listening.